Hey everyone, and welcome back to another edition of The Explainer. I am absolutely thrilled you're here today because, well, we're embarking on a truly fantastic journey. And just to be clear up front, we aren't just doing some standard dry test prep today. Oh no, we are going to be building a comprehensive guide to atomic structure and the periodic table, but we're treating it like a grand cosmic puzzle. Because honestly, that's what it is. It's the ultimate code that literally decodes the universe around us. Every single thing you can see, touch, or breathe is built entirely on the hidden architecture we're about to explore. Now, to make this incredibly practical, we're going to frame our journey today around a really fascinating challenge. Could you pass the ultimate chemistry entrance exam? We're going to look at actual university entrance exam, or UEE questions, to see just how well we can navigate these concepts. And I want you to solve these puzzles right alongside me. Think of this less as abstract chemistry and much more like a high-stakes detective story, where the clues are completely invisible to the naked eye. Okay, let's dive into this. Here is our roadmap for today. We'll start with the evolution of atomic theory, then discovering subatomic particles, and the rules of quantum mechanics. After that, we'll get super practical by mapping electron configurations, decoding the periodic table, and finally, mastering periodic trends. All right, Section 1, Evolution of Atomic Theory, going from solid spheres to subatomic complexity. You know, it's really easy to look at a modern textbook and just assume science always had the right answers. But our understanding of matter actually started out as a brilliant, yet fundamentally flawed guess. Back in the early 19th century, John Dalton proposed his famous atomic theory. He pictured atoms essentially as solid, indestructible billiard balls. He was absolutely convinced that all atoms of a specific element were completely identical in mass and size. But as science advanced, we had to adapt. Modern atomic theory realized that atoms aren't solid spheres at all. They contain even smaller subatomic particles. And honestly, more importantly, we discovered isotopes, which means atoms of the exact same element can actually have slightly varying masses. And that brings us right to our first piece of exam evidence. Take a look at this question. It asks exactly which of Dalton's postulates was disproved by modern atomic theory. Well, if you look at the first option, all atoms of the same elements are identical and have the same mass, you immediately spot the flaw. Because we now know about isotopes, we know this statement from Dalton is definitively false. Science is a living thing, right? It adapts the second new evidence, shatters old assumptions. Moving on to Section 2, Discovering Subatomic Particles. We are cracking the atom open. So we are entering this wild historical era where brilliant scientists essentially took Dalton's indestructible atom, threw it in a metaphorical particle smasher, and just cracked it wide open. Let's look at this rapid-fire history. I mean, it took humanity thousands of years to accept that atoms even existed, but just a few decades to figure out their inner workings. In 1897, J.J. Thomson used cathode ray tubes to discover the tiny, negatively charged electron. Fast forward a bit to 1911, and Ernest Rutherford realized that atoms are mostly empty space, with a super dense, positive center, giving us the concept of the nucleus. And finally, in 1932, James Chadwick discovered the elusive neutral particle hiding right inside that nucleus, the neutron. Let's see how this builds our exam-solving skills. Look at these two questions here. The one on the left asks who used the cathode ray tube to discover the electron and its charge-to-mass ratio. Boom! Based on that timeline we just covered, we know instantly that's J.J. Thomson. And on the right, the question asks who discovered the existence of neutrons. Without even breaking a sweat, we lock in James Chadwick. Having this historical framework isn't just about memorizing names, it's about deeply understanding how the pieces of the puzzle were actually found. That brings us to Section 3, the rules of quantum mechanics, the traffic laws of the microscopic world. All right, prepare to completely leave the predictable world of classical physics behind. I want you to really ponder this for a second. How do you map a particle that is everywhere and nowhere at once? Up until now, scientists thought of electrons like little planets orbiting a sun. But what happens when the planet starts behaving like a cloud of pure probability? Let's take a look. Now, what's really interesting about this transition in science is exactly how it's captured in this exam question. The question describes an atom where the hydrogen atom moves in a fixed circular orbit associated with allowable energy states. This perfectly describes Bohr's theory. Niels Bohr gave us this deeply comforting model that looked just like our own solar system. It was a massive stepping stone for sure, but it wasn't the whole truth. Electrons aren't actually confined to neat, perfectly drawn rings. Yeah, the dream of the perfect orbit was completely shattered by Werner Heisenberg. Look at this question here. The Heisenberg uncertainty principle states that it is impossible to determine both position and momentum of an electron simultaneously. Basically, if you know exactly how fast an electron is moving, you completely lose track of where it actually is. Because of this, we had to abandon Bohr's rigid orbits, and instead we embraced orbitals, which are really just 3D probability clouds where an electron is likely to be found. Which leads us perfectly to Section 4, Mapping Electron Configurations, assigning addresses to electrons. Okay, so if electrons live in these fuzzy probability clouds, how on earth do we keep track of them? Well, we basically organize them into tiny atomic apartment blocks. And to keep our apartment block orderly, we have two golden rules. The first is the Pauli exclusion principle. No two electrons in an atom can have the exact same set of 4 quantum numbers. Think of it exactly like a mailing address. No two people in the apartment building can have the exact same room and bed number. The second rule is Hund's rule. This one states that you must fill equal energy orbitals with single electrons before you start pairing them up. I always like to think of this as the roommate rule, right? If there are multiple empty bedrooms in an apartment, everyone is going to claim their own room first before they reluctantly agree to share. And this brilliantly illustrates what happens when the rules are broken. Take a close look at this diagram. We see electrons represented by these little arrows filling up the 1s and 2s orbitals perfectly fine, but look closely at the 2p orbital. Instead of placing one arrow in each of the available boxes, they've jammed 2 arrows into the very first box while leaving the third box totally empty. They completely skipped claiming their own empty rooms. Therefore, as the first option correctly states, Hund's rule has been completely violated here. Section 5. Decoding the periodic table. The macro map of microparticles. All right, we are zooming way out now. Take a moment and just look at the periodic table. When you first study chemistry, it kind of looks like a totally random, jagged castle of blocks. But its shape isn't random at all. Every single row and column is entirely dictated by how those tiny electron orbitals are filling up. The periodic table is, quite literally, a giant visual representation of quantum mechanics. The left side, the middle, the right side, they all correspond directly to those S, P, D, and F apartment blocks we just talked about. Let's actually prove it with these two questions. The one on the left gives us this incredibly daunting string of letters and numbers ending in 4d65s2. Because it finishes filling up its d orbital, it belongs squarely in the d block, which is that massive transition metal section right in the center of the table. Then, on the right, the question gives us a configuration ending in 4p5. Because the outermost electrons are in the p orbital, it belongs in the p block, on the right side of the table. So those intimidating strings of numbers, they are literally just GPS coordinates pointing to a specific neighborhood on the map. And finally, Section 6. Mastering periodic trends, predicting elemental behavior. Once you really understand the table's shape, you can instantly predict how any element will behave in the real world without ever even seeing it in a lab. Let's slow down here and look at the 3 biggest directional rules. First up, atomic radius, which is basically just the size of the atom. It actually gets smaller as you move left to right across a period, but it gets larger as you move top to bottom down a group. Then we have ionization energy, which is how hard it is to rip an electron away, and electronegativity, how greedy an atom is for electrons. Both of these do the exact opposite of size. They increase as you move left to right, and they decrease as you move top to bottom. If you lock these directional arrows into your mind, you hold the ultimate key to predicting chemical reactions. Let's test that out immediately. Look at this abstract chart here. We have a property that decreases as it goes to the right and increases as it goes down. Take a second. Which of our 3 rules fits that perfectly? If you said atomic radius, you hit the nail on the head. As atoms pack more protons in the same energy level across a period, they pull their electrons tighter, shrinking the radius. But as they add whole new energy shells moving down a group, they just balloon in size. So atomic radius perfectly matches this diagram. So the crucial point is, if you truly understand these trends, you don't even need the element names. Check out this question. It's literally just a blank grid with random letters. But using our trend rules, we can evaluate the options perfectly. Let's look at the option regarding atomic radius. It says B is greater than J, which is greater than E, which is greater than C. Looking at the grid, B is at the bottom left, the biggest area. C is at the top right, much smaller. E and J are somewhere in the middle. So mapping out B greater than J, greater than E, greater than C perfectly aligns with our rule that atoms get larger as you move down and to the left. You've just solved a really complex puzzle purely by its geographic location. How cool is that? And there you have it. We've traveled all the way from Dalton's flawed solid spheres straight through to predicting the exact behavior of elements on a completely blank grid using the mind-bending laws of quantum mechanics. It is such a massive testament to human curiosity. Which leaves me with this final thought for you to ponder. If we can predict the chaotic, invisible quantum world with such stunning mathematical precision, what other hidden rules of the universe are just out there, waiting for us to discover them? Keep questioning, keep decoding, and I'll catch you on the next explainer.